The heat hits me even before I open the insulated door, a wall of warmth so intense it feels almost liquid, pressing against my protective suit as I prepare to enter one of the most extraordinary places on Earth. I'm standing at the entrance to the Naica mine in Chihuahua, Mexico, nearly 1,000 feet below the surface, about to descend even deeper into what scientists call the Cave of Crystals, a cathedral carved not by human hands, but by time, heat, and the patient chemistry of mineral-saturated water. My suit is bulky, filled with ice packs and equipped with its own cooling system, because where I'm going, the temperature reaches 50 degrees Celsius, hot enough to cause heat exhaustion in minutes without protection. The humidity is nearly 100%, which means sweat cannot evaporate to cool you. Your body's natural cooling system simply stops working. People have fainted in there, overwhelmed by conditions that push human physiology to its absolute limits. But the reason for enduring this discomfort is worth it. Beyond this door lies one of the most stunning geological formations ever discovered, a cave filled with selenite crystals so large they defy easy comprehension. Crystals the size of trees, some reaching over 11 meters long and weighing more than 50 tons. Translucent beams of crystallized gypsum that have grown with impossible slowness over 500,000 years, creating a landscape that looks more like something from another planet than anywhere on Earth. I check my equipment one final time. Headlamp, backup lights, water supply. Hydration is critical in the extreme heat. And the timer that will remind me when I've been inside for 20 minutes. The maximum safe exposure time, even with protective gear. My guide, Juan, a geologist who has studied these caves for 15 years, gives me a thumbs up. His eyes crinkle with a smile I can't see behind his mask, but I recognize the look, the anticipation of someone about to share something they love with a newcomer. The door opens, and we step through into a transition chamber, then through another door, and suddenly I'm inside. The air is thick, almost tangible, and the heat wraps around me despite my suit. But all discomfort vanishes as my eyes adjust to what I'm seeing. Crystals everywhere. Enormous translucent beams crossing the cave in every direction, some horizontal, some diagonal, some meeting in X patterns like the crossed swords of giants. The largest crystal visible from where I stand is perhaps 10 meters long and a meter thick at its widest point, its surface smooth and slightly reflective, catching and softening the light from our headlamps. The cave itself is roughly 30 meters long and 10 meters wide, but the crystals make the space feel both larger and smaller simultaneously. Larger because of the sheer scale of individual formations. Smaller because they fill so much of the volume, creating obstacles we must carefully navigate around. The floor is uneven, partially covered in smaller crystals, and we move slowly, methodically, careful not to damage formations that took hundreds of thousands of years to create. These are selenite crystals, Juan explains, his voice slightly muffled through the breathing equipment. Selenite is a crystalline form of gypsum, hydrated calcium sulfate, the same mineral that's used to make drywall in construction, but here, under perfect conditions, it grew into these giants. I reach out carefully to touch the nearest crystal, and its surface is warm, almost hot, smooth as glass but with subtle striations running along its length, growth lines that record its formation over geological time. The crystal is remarkably clear, translucent rather than transparent, allowing light to penetrate several centimeters into its structure before scattering, giving it an internal glow that makes it seem almost alive. How did they grow this large? I ask, knowing the answer intellectually but wanting to hear Juan's explanation. to understand it in the context of standing here among them. Perfect conditions maintained for an extraordinarily long time, he says, and I can hear the awe in his voice even after all his years studying this place. This cave was completely filled with mineral-rich water, groundwater that had dissolved gypsum from surrounding rocks. The water temperature was constant at about 58 degrees Celsius, maintained by a magma chamber deeper below that's been slowly cooling for millions of years. He points to one of the massive crystals. At that precise temperature, gypsum wants to crystallize out of the water, but only very slowly. If it happened too fast, you'd get many small crystals. But here, the conditions were so stable that molecules could add to existing crystals one layer at a time, without forming new crystals. It's like, imagine building a structure where you can only add one brick per year, but you have 500,000 years to work with. The scale of time involved is staggering. These crystals began forming during the Middle Pleistocene, when Neanderthals and Homo sapiens were just beginning to diverge, when mammoths and saber-toothed cats roamed the continents. And they grew, molecule by molecule, layer by layer, in darkness and heat, completely isolated from the surface world for longer than modern humans have existed as a species. Juan leads me carefully between two massive crystals that cross near the cave floor, forming a narrow passage we must squeeze through sideways. The crystal surfaces are so close I can see my reflection distorted in them, ghostly and wavering in the lamplight. On the other side, the cave opens into a slightly larger chamber, and here the formations are even more spectacular. Crystals jutting from floor, walls, and ceiling, some meeting in the middle to create complete columns of solid selenite. The mine discovered this cave by accident in 2000, Juan continues. They were drilling to expand mining operations and broke through into the chamber. At first, they thought it was just another water-filled cavity. The mine is constantly fighting flooding from groundwater, but when they pumped it out to continue working, they found this. I try to imagine that moment of discovery, miners expecting rock and water, instead finding themselves in a crystal cathedral. The initial reports were apparently met with skepticism. Crystals this size seemed impossible. Even experienced geologists had to see it with their own eyes before they could fully believe it. But there's a tragedy in the discovery, Juan says quietly. For these crystals to grow, the cave needed to remain flooded with that mineral-rich water at a constant temperature. By pumping out the water to mine the silver ore below, we stopped the growth process. These crystals will never grow again. The statement hangs in the thick air between us. We've frozen these formations at this exact size, ended a growth process that had continued uninterrupted for 500,000 years. It's a sobering reminder of how human activities intersect with geological processes, how in seeking resources we inadvertently alter systems that operated on timescales far beyond human comprehension. Are they deteriorating now that the water's gone? I ask, concerned. Slowly, yes. In the hot, humid air, they're actually beginning to dehydrate, converting from selenite back to anhydrite, gypsum without water. You can see some surface dulling on the older exposed areas. Eventually, over decades or centuries, they'll lose their clarity and become opaque. Scientists are debating how to preserve them or whether the cave should be reflooded to halt the deterioration, but that would mean losing access. It's one of those impossible choices. Preserve the crystals in their growing environment, but lose the ability to study and witness them, or keep them accessible, but watch them slowly degrade. For now, access is strictly limited and carefully controlled, with researchers and a handful of visitors allowed in only briefly with proper equipment. I noticed something unusual about one of the crystals near me. There appear to be small, dark inclusions trapped within it, tiny pockets visible through the translucent surface. What are those? I ask, pointing. Juan moves closer, examining where I'm indicating. Fluid inclusions, small amounts of the water that these crystals grew from, trapped as bubbles inside the crystal structure as it formed. They're incredibly valuable scientifically because they preserve the exact chemistry of the groundwater at different points in time. He explains that scientists can carefully extract these fluid inclusions, a painstaking process that involves precisely breaking the crystal, and analyze the water that's been sealed inside for hundreds of thousands of years. The chemistry tells us about groundwater composition, temperature, and even allows us to date different growth layers of the crystal. But here's what's truly remarkable, Juan continues, his voice rising slightly with excitement. Some of those fluid inclusions contain living microorganisms, bacteria that have been trapped inside the crystal for up to 60,000 years, dormant but not dead. When scientists extract them carefully and provide nutrients, some of these ancient bacteria revive and begin growing again. I stare at the crystal with new wonder. Inside its structure, visible as tiny dark specks, are organisms that were alive when Homo sapiens were just beginning to migrate out of Africa, when Neanderthals still lived in Europe, when the world was gripped by an ice age, and they survived, suspended in a crystalline prison, waiting. How is that possible, I ask? 60,000 years without nutrients, without reproducing? They enter a state called sporulation or extreme dormancy, Juan explains. Their metabolism drops to nearly zero. They're not really alive in any active sense, but they're not dead either. They're waiting. And under the right conditions, the conditions we create in a lab, they can revive. It's as if they were frozen in time, though they were actually in hot water the whole period. This discovery has profound implications for understanding life's limits and possibilities. If bacteria can survive dormant for 60,000 years and revive, how long might they theoretically survive? 1,000,000 years? 10 million? And if they can survive encased in crystals on Earth, might similar preservation occur in crystals on Mars or other worlds? Mars, we know, once had liquid water on its surface and likely had groundwater systems similar to those that created these caves. If Mars had microbial life in its past, might that life still exist in dormant form, trapped in mineral deposits, waiting for conditions that would allow revival? The Naica crystals suggest it's possible. My timer vibrates. We've been inside for 15 minutes, and Juan signals that we should begin making our way toward the exit. Even with the cooling suit, I can feel the heat accumulating, my heart rate elevated from the stress my body is under. But I'm reluctant to leave, wanting to absorb every detail of this extraordinary place. As we move carefully back through the crystal forest, Juan points out features I missed on the way in. Some crystals show slight curvature along their length, bending in response to stress or minor shifts in the cave structure over time. Others have smaller crystals growing from their surfaces at different angles, secondary growth that occurred during periods when conditions changed slightly. The cave isn't static, Juan explains as we navigate between formations. The mountain above us is constantly settling, adjusting. Earthquakes occur in this region. Each time there's movement, it creates tiny stresses in the crystals. Some have fractured and healed, incorporating new material into the break. They're recording the geological history of this region in their structure. We pass a crystal that has a visible crack running through it, but the crack has been filled with new selenite growth, creating a healed seam that's slightly more opaque than the surrounding material. It's like a scar, a record of trauma and recovery written in mineral form. Near the exit passage, Juan pauses by a relatively small crystal, only about 2 meters long, and gestures for me to look closely at its base where it emerges from the cave floor. See how it's anchored? The crystal grew from a tiny seed, probably a microscopic gypsum crystal or even a dust particle that provided a nucleation point. Then, layer by layer, ions of calcium and sulfate dissolved in the water, bonded to that seed, following the atomic structure that gypsum naturally forms. The atomic structure of gypsum is what gives these crystals their distinctive shape, elongated prisms with chisel-like ends. At the molecular level, calcium ions bond with sulfate groups and water molecules in a specific three-dimensional arrangement that repeats itself billions upon billions of times, creating the macroscopic crystal we can see and touch. It's a beautiful example of how atomic scale forces and geometry scale up to create structures visible to the human eye. Every crystal in nature follows rules determined by its atomic structure, Juan continues. Salt forms cubes because of how sodium and chlorine ions pack together. Quartz forms hexagonal prisms because of silicon and oxygen bonding patterns. Snowflakes form six-sided symmetry because of the angle between hydrogen atoms and water molecules. The universe has geometry built into it at the smallest scales, and that geometry expresses itself in the shapes we see. This idea that the forms of crystals are inevitable expressions of atomic forces has always fascinated me. There's something almost philosophical about it, the way microscopic rules generate macroscopic beauty, the way structure at one scale determines structure at every larger scale. It's a principle that extends beyond crystals to many natural phenomena. The branching patterns of rivers and trees, the spiral of galaxies and hurricanes, the hexagonal cells of honeycombs. We reach the exit chamber, and I take one last look back at the crystal cave before the door closes. The view is otherworldly, massive, translucent beams crossing in every direction, catching the light, glowing from within. It looks like the interior of some vast alien geode, a hollow space lined with crystalline beauty, which, in a sense, is exactly what it is. Through the door, into the transition chamber, then finally into the cooler corridor of the mine. Even though the mine tunnel is still warm by surface standards, it feels refreshingly cool after the intense heat of the crystal cave. I begin removing my protective suit, and immediately I understand why the time limit is so strictly enforced. I'm drenched in sweat despite the cooling system, my heart is pounding, and I feel slightly lightheaded. Juan hands me a bottle of electrolyte solution. Drink. Everyone underestimates how much water they lose in there. The humidity is so high that you don't notice you're sweating because it can't evaporate. But your body is working hard to try to cool itself. I drink gratefully, feeling the cool liquid spread through me. As my body begins to recover from the heat stress, my mind is still processing what I've seen. The Cave of Crystals is one of those rare places that exceeds your imagination even when you've seen photographs and read descriptions. The scale, the clarity, the sheer improbability of such formations existing, it all combines to create a sense of wonder that's hard to articulate. There are other crystal caves in the mine, Juan says, as we begin walking back through the tunnels toward the surface. Not as spectacular as the Cave of Crystals, but each one unique. The Cave of Swords was discovered in 1910, before the Big Cave. It contains thousands of smaller selenite crystals, most about a meter long, jutting from the walls like swords. It was at a shallower depth and cooler, so the crystals grew faster and smaller. The relationship between growth rate and crystal size is counterintuitive until you understand the chemistry. Faster growth means more nucleation sites, more competition between crystals, resulting in many small crystals rather than a few giants. Slow growth means fewer nucleation events and more time for existing crystals to incorporate material, allowing them to reach enormous sizes. The mine won't operate forever, Juan continues, his voice taking on a somber tone. Silver production is declining, and maintaining the pumps that keep the deeper levels dry is expensive. When mining ends, probably within the next decade or two, the company will stop pumping and groundwater will refill all these chambers. The crystal cave will be underwater again. The thought of the cave reflooding is bittersweet. On one hand, it means the crystals will stop deteriorating, preserved once again in the mineral-rich water that created them. They might even resume growing, adding new layers over the centuries and millennia to come. But it also means that direct human access will end, that this window into Earth's crystalline artistry will close, perhaps forever. Will the crystals start growing again if the cave refloods? I ask, as we walk through the mine tunnel, our headlamps creating moving shadows on the rock walls. Juan considers this carefully. It depends on whether conditions return to what they were. The magma chamber below is still cooling. That's an ongoing process that will continue for millions of years. But the exact temperature and chemistry that produced those giants required very specific conditions. If the water temperature is even a few degrees different, or if the mineral saturation changes, the crystals might not grow the same way. They could grow faster and less perfectly, or they might stop growing altogether if conditions aren't right for gypsum crystallization. We pass through a section of tunnel where the rock walls show clear evidence of the mining operation. Drill holes, blast marks, the rough surfaces where explosives fractured the stone to extract silver ore. The contrast with the natural perfection of the crystal cave is striking. Here, humans have imposed their will on the rock through force. In the cave, nature worked with patience and precision, building structures we can barely replicate even with all our technology. The Naica mine itself has been operating since the colonial period, with modern industrial mining beginning in the early 20th century. It's part of a rich mineral belt in northern Mexico, where geological processes concentrated valuable metals in veins and pockets within the rock. The same hydrothermal activity that created the crystal caves also deposited silver, lead, and zinc in economically valuable quantities. The crystals and the silver ore are related, Juan explains. Both were created by hot fluids moving through the rock, dissolving minerals in one location and depositing them in another. The difference is that silver requires more extreme conditions, higher temperatures, different chemistry. The crystals formed in a relatively gentle environment. The metal ores formed under more violent circumstances, with superheated fluids under pressure forcing their way through cracks in the bedrock. This is the story of ore deposits throughout the world. They're almost always connected to hydrothermal activity, to water heated by magma or deep burial, moving through rock, dissolving and redepositing minerals. The same processes that create beautiful crystals also create the concentrated metal deposits that human civilization depends on. We mine these deposits, extract the metals, and use them to build everything from electronics to bridges to solar panels. But metal ores are finite. Each deposit represents millions of years of geological concentration, and once mined, those atoms are dispersed into human artifacts, landfills, recycling streams. We're living off Earth's geological savings account, accumulated over deep time, and spending it rapidly. This is why recycling becomes increasingly important. The easily accessible ore deposits are being depleted, and future generations will need to recover metals from what we've already extracted rather than finding new virgin deposits. We reach an elevator shaft a metal cage that will carry us back toward the surface. As it rises, Juan continues sharing knowledge, unable to contain his enthusiasm for the subject even after years of study. Gypsum is everywhere on Earth, he says. It forms whenever seawater evaporates in enclosed basins, leaving behind dissolved minerals. The white sands of White Sands National Park in New Mexico? That's gypsum, weathered into sand grains. The alabaster used in ancient sculptures? Gypsum. Even the drywall in most modern buildings, that's gypsum mixed with paper and other materials. But nowhere else on Earth, nowhere that we've discovered at least, has gypsum-formed crystals as large as those in the Naica caves. The combination of factors was too specific, too perfectly balanced. The right temperature maintained for the right duration, with the right water chemistry and the right degree of isolation from disturbance. It's a geological jackpot, a convergence of favorable conditions that may be unique on our planet. Have similar caves been found elsewhere? I ask, as the elevator continues its ascent. Nothing comparable, Juan replies. There are large crystal caves in other locations. The Cave of the Crystals in Pulpe, Spain, has beautiful selenite crystals up to 2 meters long. The giant quartz crystals in Brazil can be impressive, but nothing matches Naica for sheer size. These are likely the largest natural crystals of any mineral that have ever been found on Earth. The elevator reaches an upper level, and we transfer to another that will take us the rest of the way to the surface. The temperature is gradually dropping as we rise, becoming more comfortable with each level. I can feel my body relaxing, my heart rate returning to normal, the stress of the extreme heat environment fading. Juan checks his watch. We have about an hour before the next authorized entry window for the cave. There's something else I want to show you. One of the other crystal chambers that's more accessible and doesn't require the protective suits. It'll give you a sense of how variable these formations can be, even within the same mind system. We emerge into daylight, or what passes for daylight, in the deep mine shaft. It's still artificial light, but brighter and cooler than the tunnel illumination. We're perhaps 300 meters below the surface, in a network of chambers and passages carved over decades of mining operations. Juan leads me through a series of tunnels, and I notice the rock changing. The walls here show beautiful banding, layers of different minerals deposited at different times, each band telling a story of changing conditions in the ancient past when these rocks were forming. Some bands are rich in iron, stained rust red. Others are nearly white, composed mostly of limestone or gypsum. Still others show dark mineral concentrations, possibly manganese or other trace elements. We arrive at a smaller chamber, and even without the extreme heat, the sight is breathtaking in a completely different way. This cave, Juan tells me it's called the Ice Palace, though there's no ice here, contains clusters of smaller selenite crystals, most between 0.5 meter and 1 meter in length, arranged in spectacular rosette patterns. They emerge from the walls and ceiling in radiating groups, like frozen flowers or stars, each crystal perfectly transparent and catching the light from our lamps. These formed under different conditions, Juan explains. Cooler water, faster growth. You can see how the crystals competed with each other. They're thinner, more blade-like, growing outward from central points. In the main cave, there was enough time and space for individual crystals to grow massive without much competition. Here, dozens of crystals nucleated close together and grew simultaneously. I move closer to examine one of the rosettes, and the detail is extraordinary. Each individual crystal blade is flawless, with razor-sharp edges and perfectly flat faces that meet at precise angles. The transparency is such that I can see through multiple overlapping crystals, creating complex patterns of refraction and reflection. It's like looking into a geometric flower made of glass and light. Can I touch them? I ask, knowing how delicate crystal formations can be. Carefully, yes. They're harder than you might think. Gypsum has a hardness of 2 on the Mohs scale, which means you can scratch it with your fingernail, but these crystals are thick enough to be relatively sturdy. Just avoid putting pressure on the thin edges or tips. I reach out and gently place my palm against the flat face of one of the larger crystals in the rosette. It's cool to the touch, surprisingly so, as if it's holding on to some memory of the cold water it might have formed in, though I know this is just because crystal is denser than air and conducts heat away from my hand more efficiently. The surface is perfectly smooth, molecular layers of calcium sulfate arranged so precisely that there's no roughness at any scale larger than atoms. Light behaves in interesting ways in crystals, Juan says, positioning his headlamp to shine through one of the crystal blades. The light doesn't just pass straight through, it bends, refracts, splits into different paths as it encounters the boundaries between crystal and air. Some of the light reflects internally, bouncing between the crystal faces before finally emerging at unexpected angles. Crystals can be birefringent, he continues. That means they split light into 2 rays that travel at different speeds through the material. Calcite is famous for this. If you place a clear calcite crystal over text, you see double. Gypsum does this too, though the effect is subtler. It's because the crystal structure isn't symmetrical in all directions. Light moving along one axis of the crystal encounters a different arrangement of atoms than light moving along another axis. This property, birefringence, has practical applications in geology and material science. Geologists use it to identify minerals by examining thin slices of rock under polarized light microscopes, where birefringent minerals produce distinctive colors and patterns. Engineers use it to detect stress in transparent materials like glass or plastic, since stress changes how light propagates through the material. Even some animals, like mantis shrimp, use birefringent crystals in their eyes to detect polarized light, giving them a way of seeing that humans lack entirely. The cave walls here show something else interesting: small pockets and vugs where crystals have formed in isolation, creating tiny perfect chambers lined with crystal points like miniature geodes. Some are small enough to cup in your hand, others large enough to put your head inside, each one a complete crystalline world in miniature. These vugs form when there's a cavity in the rock, maybe from a dissolved fossil, or a gas bubble in volcanic rock, or just a gap between rock layers, Juan explains. When mineral-rich water fills the cavity and conditions are right for crystallization, crystals grow inward from all sides, competing to fill the space. If the cavity is sealed off from water flow, you can get especially perfect crystals because there's no contamination, no particles settling on growing faces to disrupt their geometry. I peer into one of the larger vugs, shining my headlamp inside, and it's like looking into a crystal cave within a cave. Hundreds of small crystal points, each one geometrically perfect, line every surface, creating a glittering hollow that seems to capture and multiply the light. There's something deeply satisfying about these natural forms, something that speaks to an aesthetic sense I didn't know I had. The human brain seems hardwired to appreciate symmetry, geometry, pattern, perhaps because these qualities often indicate something important about the world, something worth paying attention to. Humans have been fascinated by crystals for all of recorded history, Juan muses. Ancient peoples attributed magical or healing properties to them. Medieval alchemists thought they could unlock the secrets of transmutation by understanding crystalline forms. Even now, despite all our scientific understanding, there's something about crystals that captures imagination in ways that other geological formations don't quite match. He's right, I realize. There's something almost hypnotic about crystals. The way they embody mathematical perfection, the way they transform light, the way their surfaces and edges seem impossibly precise. They're proof that nature, following nothing but physical laws and given enough time, can create beauty that rivals anything human artists and architects can imagine. Part of it is the rarity, Juan continues. Most rock is cryptocrystalline or microcrystalline, made of crystals too small to see without magnification. When we encounter crystals large enough to see clearly, especially perfectly formed ones, it's exceptional. And when we find them at the scale of the Naica giants, it's almost unprecedented. We spend time exploring the ice palace, examining different formations, discussing the minor variations in crystal habit, the specific shape crystals take based on subtle differences in growth conditions. Some crystals here are stubby and thick, others elongated and needle-like. Some have perfectly flat termination faces, others are more irregular. Each variation tells a story about water temperature, mineral concentration, growth rate, the presence of impurities. As we prepare to leave the ice palace, Juan pauses by a particularly unusual formation, a crystal cluster, where one large selenite blade has smaller crystals growing perpendicular to its surface, creating a kind of crystalline tree structure. This is what we call epitaxial growth, he explains. The smaller crystals are using the surface of the larger one as a template, but they're oriented differently because conditions change between when the large crystal formed and when the small ones nucleated. It's a visible record of time and changing conditions, written in mineral form. The large crystal represents one phase of the cave's history. The smaller ones, a later phase when temperature or chemistry shifted just enough to favor a different crystal orientation. Reading these structures is like reading tree rings or ice cores. Each layer, each feature, carries information about the environment that created it. We make our way back through the mine tunnels, and Juan shares stories of the discoveries here, the challenges of working in such extreme conditions, the careful balance between mining operations and scientific preservation. The Naica mine has become important to science far beyond its economic value, attracting researchers from around the world to study not just the crystals, but also the extremophile microorganisms, the geochemistry, the processes that create such formations. There's been discussion about turning the crystal caves into a protected site, maybe even a museum eventually, Juan tells me. But the logistics are incredibly challenging. How do you preserve access to something that requires such extreme protective measures? How do you balance scientific research with potential tourism? And how do you do any of this when the caves are at the bottom of an active mine that will eventually flood? These aren't easy questions. The crystal caves represent natural heritage of global significance, but they exist in a context that makes simple preservation strategies impossible. The heat and humidity make long-term human presence difficult. The need for continuous pumping to keep water out is expensive and energy-intensive, and ultimately, the mine's economic purpose takes precedence. This is private property, and the crystal caves were discovered incidentally to mining operations. We reach a chamber where geologists have set up monitoring equipment, sensors measuring temperature, humidity, air composition, even subtle vibrations in the rock. All of this data feeds into studies of how the caves are changing now that they're no longer water-filled, how quickly the crystals are deteriorating, whether intervention might be possible or advisable. One proposal is to create a controlled environment, Juan explains, gesturing to the equipment. Seal the cave, regulate temperature and humidity, perhaps even reintroduce mineral-saturated water in a controlled way. Essentially, create an artificial version of the natural conditions that form the crystals. But it would be expensive, technically challenging, and there's no guarantee it would work long-term. The alternative is documentation, detailed 3D scanning, chemical analysis, collection of samples for museums and research institutions. If the caves are going to be inaccessible in the future, at least preserve the data, preserve the knowledge, preserve examples of what existed here. It's not ideal, but it may be the most realistic option. As we walk, I think about the broader question of geological preservation. Earth is constantly changing. Mountains rise and erode, coastlines shift, caves form and collapse, minerals crystallize and dissolve. The landscapes we see today are temporary snapshots in an ongoing process that operates on time scales far longer than human civilization. Should we try to preserve specific geological features? Can we even meaningfully do so? Or should we accept that change is fundamental to geology, that the crystal caves are themselves temporary, and that their eventual reflooding and inaccessibility is simply part of their natural cycle? There's no clear answer. Different people prioritize differently. Scientists want continued access for research. Conservationists want protection from damage. Mining companies need to balance preservation with economics, and local communities have their own relationships with these features. Every natural wonder on Earth exists within complex networks of interests and values that don't always align. We reach the main shaft and begin the final ascent to the surface. As we rise, I feel the air changing, cooler, drier, more familiar. The extreme environment of the deep mine, with its heat and humidity and extraordinary formations, is giving way to the ordinary world above. But ordinary feels relative now. After witnessing the Crystal Cathedral, the surface world seems both more mundane and more miraculous. Mundane because it lacks those spectacular formations. Miraculous because it's the world where life thrives, where complexity proliferates, where geology and biology intersect in countless ways. The elevator reaches the surface, and we step out into the afternoon light of the Chihuahua Desert. The contrast is immediate and stark. From the enclosed artificial environment of the mine to the open space and natural sunlight above. The desert here is beautiful in its own way, though so different from the subterranean wonders below. Mountains rise in the distance, their slopes covered in sparse vegetation adapted to heat and aridity. The sky is vast and blue, scattered with white clouds. The desert and the caves are connected, Juan says, following my gaze. The groundwater that filled the crystal caves comes partly from here, rain falling on these mountains, seeping into the ground, percolating down through rock over thousands of years, getting heated by geothermal gradients, dissolving minerals, and eventually filling those chambers deep below. Everything is part of the same hydrological cycle, the same system of water moving through Earth's crust. We walk away from the mine entrance toward a small research station set up nearby, where scientists studying the caves have established a base of operations. The building is modest, just a few rooms with equipment, computers, specimens, and reference materials. But it represents years of dedicated research, hundreds of trips into the caves, thousands of measurements and observations. Inside, Juan shows me samples of crystals carefully extracted for study, some small enough to hold in your hand, others requiring 2 people to lift. Each is cataloged with precise information about where it came from, what depth, which chamber, when it was collected. The care taken in documentation reflects the understanding that these samples are irreplaceable, that future scientists will want to know their exact provenance. One sample particularly catches my attention, a crystal section that's been cut and polished to reveal its internal structure. The cut surface shows growth bands, subtle variations in clarity and color that represent different phases of crystal formation. Some bands are nearly perfectly clear, others slightly cloudy, others contain visible inclusions of tiny mineral grains or fluid bubbles. We can analyze these bands chemically, Juan explains, measuring trace elements, isotope ratios, even organic molecules. Each band is like a snapshot of the groundwater chemistry at the time that material was deposited. By working from the center outward, we're essentially reading backward through time. The innermost material is oldest, the outermost is youngest. The technology for this kind of analysis has advanced enormously in recent decades. Instruments called ion microprobes can measure chemical composition at scales of micrometers, allowing researchers to analyze individual growth bands in detail. Mass spectrometers can detect elements present at parts per billion or even parts per trillion. Techniques borrowed from biology can identify and analyze organic molecules and microbial DNA preserved within the crystals. One of the most interesting findings, Juan continues, is that the growth wasn't continuous. There were periods when the crystals grew rapidly and periods when growth slowed or stopped entirely. We can correlate these with known climatic events, ice ages, warm periods, changes in precipitation patterns that affected groundwater recharge. The crystals are recording not just local conditions, but regional and even global climate. This connection between cave formations and surface climate is seen in many geological contexts. Stalactites and stalagmites in caves around the world preserve climate records in their growth rings, much like trees. Coral reefs record ocean temperature and chemistry in their skeletons. Even the sediments at the bottom of lakes and oceans contain layer-by-layer records of changing environmental conditions. Earth is constantly writing its own history, and learning to read that history is one of geology's great achievements. On one of the workbenches, I notice a microscope set up with what appears to be a thin section of crystal mounted on a glass slide. Juan sees my interest and gestures for me to take a look. This is a sample we're studying for fluid inclusions, those pockets of ancient water trapped in the crystal structure. I peer through the microscope and see an enlarged view of the crystal's interior. What appeared clear to the naked eye reveals itself as containing numerous tiny bubbles and irregular spaces, each one a microscopic time capsule. Some contain just water, others have small gas bubbles, and a few show what might be tiny particles of organic matter or mineral crystals that were trapped when the selenite was forming. We've found some remarkable things in these inclusions, Juan says with evident excitement. Besides the bacteria I mentioned earlier, we found organic molecules that tell us about what kind of microbial communities existed in the groundwater. We found mineral crystals that don't exist in the surrounding rock, suggesting they precipitated from the water itself. We've even found traces of gases like methane and hydrogen sulfide that indicate what kinds of chemical reactions were happening deep in the groundwater system. The presence of methane is particularly interesting because it suggests microbial activity. Some microorganisms produce methane as a byproduct of their metabolism, breaking down organic matter in oxygen-poor environments. Finding methane in fluid inclusion suggests that the groundwater system wasn't sterile, but hosted active microbial communities. These microbes were living in the dark, in hot water under pressure, feeding on dissolved minerals and organic matter. an ecosystem completely independent of sunlight, similar to those found around deep-sea hydrothermal vents. The microbes we've revived from the crystals are chemolithotrophs, Juan explains. That means they get their energy from chemical reactions involving minerals rather than from organic food or sunlight. They can oxidize sulfur compounds, iron, manganese. They're essentially eating rocks. Or rather, they're facilitating chemical reactions that release energy they can use. These chemolithotrophic bacteria represent one of Earth's most ancient forms of life. Before photosynthesis evolved, before oxygen accumulated in the atmosphere, before complex life of any kind, there were microbes living off the chemistry of rocks and water. They're still here, still thriving in environments that would kill most other organisms, still demonstrating that life is fundamentally about energy extraction and that any environment with available energy can potentially support life. Juan pulls up some images on his computer, microscope photographs of the bacteria cultured from crystal inclusions. They're simple organisms, single cells, some spherical, some rod-shaped, some arranged in chains or clusters. Under certain lighting conditions, some of them glow with bioluminescence, producing their own light through chemical reactions, perhaps as a byproduct of their metabolism or possibly as a form of communication. Bioluminescence in these bacteria is puzzling, Juan admits. In the ocean, bioluminescent organisms use light for various purposes, attracting prey, confusing predators, finding mates, communicating. But in the complete darkness of groundwater systems, those purposes don't apply. It's possible that the light production is just a side effect of their chemistry, not adaptive in itself. Or maybe it serves some function we don't yet understand. The afternoon light streaming through the research station windows reminds me that an entire world exists above these underground marvels, a world operating on different timescales, different rhythms. Juan offers me water, and we sit for a moment, the cool liquid a welcome relief after the intensity of the cave visit. "There's something I want to show you before you leave," Juan says, pulling out a tablet and opening a folder of images. These are photographs taken in the Cave of Crystals over the past 20 years, from shortly after its discovery until now. Watch what happens. He arranges the images in chronological sequence and begins scrolling through them slowly. At first, the changes are subtle, barely perceptible differences in the crystal surfaces. But as the sequence continues, the deterioration becomes more apparent. Crystals that were flawlessly transparent in early images show increasing surface opacity in later ones. Some have developed a chalky white coating. Others show fine cracks that weren't present initially. This is what happens when selenite dehydrates, Juan explains quietly. It's converting back to anhydrite, gypsum without its water molecules. The process is slow by human standards, but rapid by geological standards. In another 50 years, if nothing changes, many of these crystals will have lost much of their clarity. The images are sobering, a visual reminder that preservation isn't just an abstract concern, but an urgent practical reality. Every year that passes sees more deterioration, more loss of the pristine quality that made these formations so extraordinary. It's like watching a slow-motion tragedy, the gradual degradation of something irreplaceable. Is there any way to reverse it? I ask, though I suspect I know the answer. Not without reflooding the cave with mineral-saturated water at the right temperature, Juan replies. And even then, we're not certain the crystals would recover. Dehydration might have changed their structure enough that they can't simply reabsorb water. We're in somewhat uncharted territory. No one has studied selenite crystals this large or this old, under these specific conditions before. He shows me another set of images, these from a different crystal cave that was discovered and drained decades earlier, before modern preservation concerns were well understood. The crystals there have deteriorated significantly, their surfaces completely opaque, some showing substantial structural damage. It's a preview of what might happen to the cave of crystals if intervention doesn't occur. The mining company has been cooperative, Juan continues, allowing research access, supporting some preservation studies. But they're a business, not a conservation organization. When the economics no longer justify the mining operation, they'll stop pumping water, and that will be that. We're trying to build support for some kind of long-term preservation plan, but it's complicated. Politically, financially, technically. I understand the frustration in his voice. Scientists often find themselves in positions where they can identify problems clearly, but lack the resources or authority to solve them. The crystal caves are important scientifically and aesthetically, but they exist within economic and political systems that prioritize other values. Finding alignment between these different value systems is challenging. What about creating a replica? I ask. Not to replace the original, but as a way of preserving the experience, the knowledge, for future generations who won't be able to visit? Juan nods thoughtfully. There have been proposals. High-resolution 3D scanning could capture every detail of the cave and crystals, creating digital models accurate to millimeters. Those models could be used to create physical replicas using various fabrication techniques or immersive virtual reality experiences. It's not the same as being there, but it's something. He's right that it's not the same. The heat, the humidity, the physical presence of those massive crystals, the knowledge that you're standing in a natural formation 500,000 years in the making, these qualities can't be fully replicated. But documentation and replication preserve something valuable nonetheless, making the knowledge accessible to students, researchers, and the curious public who will never have the opportunity to descend into those extreme depths. We move to another section of the research station where core samples are stored, cylindrical sections drilled from the cave walls and floor, showing the rock that hosts the crystal chambers. Juan pulls out one core and points to distinct layers visible in the rock. This is limestone. He indicates a pale gray band deposited as marine sediment about 120 million years ago, when this region was covered by a shallow tropical sea. And this, he points to a darker layer, is shale, formed from mud, that accumulated when the sea was deeper or when rivers were bringing more sediment from the land. The rock beneath the caves tells its own story, one that extends back far before the crystals formed. This region has experienced dramatic changes over geological time. Ancient seas advancing and retreating, mountains rising through tectonic forces, erosion stripping away thousands of meters of rock, volcanic activity bringing molten rock close to the surface, and finally, the groundwater circulation that created the crystal caves. Juan traces his finger along the core sample, pointing out smaller features I would have missed. Tiny fossils embedded in the limestone, each one a creature that lived and died in that ancient sea. Some are fragments of shells. Others appear to be trace fossils, burrows and tracks left by organisms moving through the seafloor sediment before it turned to stone. Every layer of rock is a graveyard and a library, Juan says quietly. The fossils tell us what lived here, which tells us about the environment, water depth, temperature, salinity, oxygen levels. The mineral composition tells us about chemistry and climate. The sediment grain size tells us about energy levels, whether this was a calm lagoon or a wave-swept shoreline. He shows me another core section where the layering is disrupted. The neat, horizontal bands are broken and tilted at angles. This is a fault, he explains. At some point, after these rocks formed, tectonic forces cause them to fracture and shift. You can see how the layers don't line up across the fault plane. This kind of fracturing is actually important for forming crystal caves because it creates pathways for water to flow through the rock. Without these fractures, the groundwater system that created the crystals wouldn't exist. Water needs permeability, spaces to move through, and solid, unfractured rock is nearly impermeable. Faults, cracks, dissolved cavities in limestone, and the spaces between rock layers all create the pathways that allow water to circulate deep underground, get heated by geothermal gradients, dissolve minerals, and eventually deposit them as crystals in favorable locations. The entire cave system is structurally controlled, Juan continues. The chambers formed where multiple fractures intersected, creating larger open spaces. The crystal orientation sometimes reflects the stress directions in the rock. Crystals growing preferentially along planes where there's slightly more room or where water flow was stronger. This relationship between structure and mineralization is fundamental to understanding ore deposits in crystal caves worldwide. Geologists searching for minerals learn to read the structural geology, identifying fault zones, fold axes, places where different rock types meet, because these are the locations where hydrothermal activity is most likely to have concentrated valuable materials. Juan checks his watch and smiles. We have one more thing to do before evening. There's a spot about 2 kilometers from here where the geology is exposed at the surface. No mine shaft required. It'll give you a different perspective on the same processes we've been discussing. We gather supplies, water, hats for sun protection, field notebooks, hand lenses for examining rocks up close, and set out into the desert. The afternoon sun is intense, but not unbearable, and the walk is pleasant, giving me time to process everything I've seen and learned today. The landscape here is quintessentially Chihuahuan desert. Sparse vegetation consisting mainly of drought-adapted shrubs, creosote bush, various cacti including impressive barrel cacti and prickly pear. The soil is rocky, with desert pavement in places where wind has blown away finer particles, leaving a mosaic of stones. In the distance, mountains rise with exposed rock faces showing dramatic geology. Folded layers, intrusions of different rock types, the visible evidence of Earth's dynamic history. Juan leads me to an outcrop where pale rock protrudes from the desert floor. This is the same limestone formation that hosts the crystal caves below, he explains. But here at the surface, it's been weathered by rain, wind, temperature changes, chemical reactions with the atmosphere. Notice how different it looks from the fresh rock in the mine. He's right. The surface rock is rougher, pitted with small holes, stained with iron oxide in places, covered with lichens in others. The sharp edges and clear layering visible in mine exposures are softened here by millions of years of weathering. It's a reminder that rock at the surface and rock underground exist in very different chemical and physical environments. Look closely here, Juan says, pointing to a particular section of the outcrop. Small crystals are visible growing in cavities in the rock, not selenite, but calcite, another form of calcium carbonate. They're much smaller than the cave giants, most just a few millimeters across, but they're perfectly formed, transparent rhombohedra, catching the sunlight. These formed recently, within the last few thousand years probably, Juan explains. When it rains, water seeps into the rock, dissolves a tiny amount of calcium carbonate, then evaporates, depositing the dissolved material as new crystals. It's the same fundamental process as in the caves, just operating at a much smaller scale and different conditions. I examine the tiny calcite crystals with a hand lens, marveling at their geometric perfection despite their small size. Each face is flat and smooth, each angle precise, following the same crystallographic rules that govern crystal formation everywhere in the universe. Whether forming over millennia in a hot cave or over years in a surface crack, crystals obey their inherent geometry. Juan sits on a flat boulder, gazing toward the mountains, and I join him. The desert is quiet, except for the occasional bird call and the whisper of wind through the sparse vegetation. There's a peacefulness here that feels timeless, though I know the landscape is constantly changing, just too slowly for human senses to perceive directly. This is what I love about geology, Juan says after a moment of companionable silence. It teaches you to see time differently. That mountain, he points to a peak in the distance, looks permanent, eternal, but it's being worn down, grain by grain, molecule by molecule, constantly changing. In a few million years, it'll be significantly lower. In 100 million years, it might be gone entirely, eroded to sea level. And yet, Juan continues, new mountains are rising elsewhere, pushed up by tectonic forces. The Himalayas are still growing, gaining several centimeters per year as India continues to collide with Asia. The Atlantic Ocean is widening as new seafloor forms at the mid-Atlantic ridge. Everything is in motion. Everything is temporary when viewed on geological timescales. This perspective shift is one of geology's greatest gifts, the ability to see the world as dynamic rather than static, to understand that the landscapes we inhabit are momentary configurations in an ongoing process of planetary evolution. Mountains rise and erode, seas advance and retreat, continents drift across the globe, species evolve and go extinct. And through it all, rocks record the history, preserving evidence that allows us to reconstruct what happened. The crystal caves are temporary too, I say, completing the thought. They formed under specific conditions that eventually changed. Now they're deteriorating. Eventually, they'll be reflooded or perhaps destroyed entirely. They're just one brief chapter in the ongoing geological story of this region. Juan nods. Exactly, which doesn't make them less valuable or less worth preserving. If anything, their impermanence makes them more precious. We're privileged to exist at the same time they exist, to be able to witness them. That's a gift we should honor. We sit quietly for several minutes, watching the sun descend toward the mountains, the light taking on the warm, golden quality of late afternoon. Shadows lengthen across the desert floor, and the temperature begins to drop from its midday peak. I think about the journey down into the earth this morning, the encounter with those massive crystals, the heat and humidity of that extreme environment, and now this peaceful moment on the surface under open sky. Tell me about the bacteria you've been studying, I say, curious to hear more about the life forms trapped in the crystals. What have they revealed about survival limits? Juan's face lights up with renewed enthusiasm. They're extraordinary organisms. Some of them have been dormant for so long that they represent ancient lineages. Their DNA sequences show they diverged from their nearest modern relatives tens of thousands of years ago. When we revive them and culture them in the lab, they grow slowly, adapted to the hot temperatures they came from. We have to incubate them at 40 to 50 degrees Celsius, conditions that would kill most bacteria. He explains that these extremophiles produce specialized proteins, heat shock proteins and chaperones, that protect their cellular machinery from damage at high temperatures. They also have unusual membrane lipids that remain functional when normal cell membranes would become too fluid. Their DNA repair mechanisms are enhanced because heat causes more DNA damage, requiring constant maintenance. But the most remarkable thing is their metabolic flexibility, Juan continues. In the groundwater environment, resources are limited and sporadic. These bacteria can switch between different energy sources depending on what's available. If sulfur compounds are present, they oxidize sulfur. If iron is available, they use iron. They can even use hydrogen gas, which is produced naturally when water reacts with certain minerals. This metabolic flexibility is key to survival in extreme environments. Specialists might be more efficient at exploiting a specific resource, but generalists can survive when conditions change. In the unpredictable environment of deep groundwater systems, flexibility is more valuable than efficiency. We've also found that some of these bacteria form biofilms, communities where individuals are embedded in a self-produced matrix of polymers, Juan adds. The biofilm provides protection from environmental stress and allows the bacteria to cooperate, sharing nutrients and genetic material. It's a survival strategy that's incredibly ancient. Some of Earth's oldest fossils are stromatolites, layered structures built by bacterial biofilms billions of years ago. The conversation reminds me how much we're still learning about life on Earth. How many undiscovered species likely exist in extreme environments we've barely begun to explore. The deep subsurface, the pores and cracks in rocks kilometers below our feet, might host as much biomass as exists on the surface, all of it microbial, all of it adapted to conditions we once thought incompatible with life. These discoveries have implications beyond Earth, I observe. If life can survive in hot groundwater systems here, similar environments on other worlds become interesting targets for exploration. Absolutely, Juan agrees. Mars almost certainly had groundwater systems in its past and might still have them in some locations. Europa and Enceladus have subsurface oceans. Even asteroids might have had liquid water in their interiors for periods in the early solar system. Anywhere liquid water existed for a significant time is potentially a habitat for life. The sun touches the mountain peaks now, and the sky begins to take on the colors of sunset, oranges and pinks and purples spreading across the western horizon. The desert landscape seems to glow in the warm light, and I feel a deep contentment, a sense of connection to this place and to the larger story of Earth and life and exploration that we've been discussing. We should head back, Juan says reluctantly. It'll be dark soon, and while the walk is straightforward, it's better to do it with good light. We gather our things and begin the return journey to the research station. As we walk, Juan points out features in the landscape, a particularly well-preserved fossil locality, an area where mineral veins outcrop at the surface, a distant volcanic cone that's been extinct for millions of years but still stands as testament to past activity. The walk back takes on a meditative quality as the desert transitions from day to evening. The temperature drops noticeably and the air feels cleaner, crisper. Small creatures begin to emerge, a lizard scurrying across our path, insects taking flight in the cooling air, somewhere in the distance the call of a poorwill, a nightjar that's one of the few birds known to enter true hibernation during cold periods. The desert has its own rhythm, Juan observes. During the heat of day, most life retreats, hides, waits. But as evening comes, the desert wakes up. It's an adaptation to temperature extremes. Avoid the heat. Be active when conditions are more favorable. This pattern of temporal niche partitioning is common in harsh environments. In the deep ocean, some creatures migrate vertically each day, rising toward the surface at night when predators are less visible, descending to depth during daylight. In polar regions, life concentrates its activity during the brief productive season and goes dormant during the long, dark winter. Life finds ways to work around constraints, to exploit the windows of opportunity that exist even in challenging places. We crest a small rise, and the research station comes into view below, lights beginning to glow in the gathering dusk. Smoke rises from a chimney. Someone is cooking dinner. The scene is homey and welcoming, a small outpost of human presence in the vast desert landscape. As we approach, I notice a group of people gathered outside, setting up what appears to be a telescope. Juan sees my curiosity and smiles. Thursday evening is astronomy night. Some of the researchers are amateur astronomers, and out here, far from city lights, the sky is spectacular. The combination is perfect: a day spent exploring Earth's interior depths, an evening observing the cosmic depths above. Both pursuits are about understanding our place in larger systems, about recognizing that we exist in the middle of a vast range of scales, from subatomic particles to galactic superclusters. We join the group as they finish setting up the telescope, a substantial instrument on a computerized mount. One of the astronomers, a woman named Elena, who studies the geochemistry of meteorites during the day, explains that they are planning to observe Saturn, which is well placed in the evening sky. The connection between astronomy and geology is closer than many people realize, Elena says, as she calibrates the telescope. Meteorites are rocks from space, but we study them with the same techniques we use for Earth rocks. They tell us about the formation of the solar system, the conditions in the early solar nebula, the processes that built planets. She's right. Some of the most important clues about Earth's formation come not from studying Earth itself, but from studying meteorites, fragments of asteroids that preserve material from the solar system's earliest days. Earth has been too geologically active, recycling its rocks through plate tectonics and erosion to preserve much original material. But asteroids, being smaller and less active, retain samples of the primordial solar system. The telescope beeps, indicating it's aligned, and Elena invites me to look through the eyepiece. I lean in and see Saturn hanging in space, its famous rings clearly visible, along with several of its moons as tiny points of light nearby. The view is breathtaking. This distant world, nearly 1 billion kilometers away, rendered visible and tangible through the telescope's optics. Those rings are made mostly of water ice, Elena explains. Countless particles ranging from dust grains to house-sized chunks, all orbiting Saturn in a thin disk. They're probably the remnants of a moon that was torn apart by tidal forces or destroyed by an impact. The rings won't last forever. They're being slowly depleted as particles fall into Saturn's atmosphere or are knocked out of orbit. Scientists estimate Saturn's rings are perhaps only a few 100 million years old, relatively young by solar system standards, and will be gone in another 100 million years or so. We're living at a time when Saturn has rings, but that's a temporary condition. Titan is visible too, Elena says, adjusting the telescope slightly. Saturn's largest moon, the only moon in the solar system with a substantial atmosphere. Through the eyepiece, I can see Titan as a tiny orange disk, distinctly different from the icy white of Saturn itself. Titan is extraordinary, larger than the planet Mercury, with an atmosphere denser than Earth's, composed mainly of nitrogen with methane and other hydrocarbons. Its surface temperature is negative 179 degrees Celsius, cold enough that water ice is as hard as rock and methane exists as a liquid, forming lakes and rivers and rain. Titan might have the ingredients for life, Elena continues, though life very different from anything on Earth. It has liquid solvent, methane instead of water. It has organic chemistry, The atmosphere produces complex organic molecules that rain down onto the surface. It has energy sources, sunlight, although weak at Saturn's distance, and possibly chemical energy from reactions between surface materials. The possibility of methane-based life is speculative, but scientifically intriguing. All life on Earth uses water as a solvent, but water's properties aren't unique. Other liquids could potentially serve similar functions. Methane at Titan's temperatures behaves similarly to how water behaves at Earth's temperatures, existing as solid, liquid, and gas depending on conditions. Could evolution work with methane instead of water? Could there be Titan organisms metabolizing in ways completely alien to Earth biochemistry? We take turns at the telescope as Elena adjusts it to show different celestial objects. Jupiter, with its great red spot visible as a pale oval, the Andromeda Galaxy appearing as a faint smudge of light representing 1,000,000,000,000 stars 2.5 million light-years away, the Pleiades star cluster, with its distinctive pattern of bright blue stars embedded in wisps of reflection nebula. Each view prompts discussion about the science behind what we're seeing. Jupiter's great red spot is a storm system larger than Earth that's been raging for at least several centuries, possibly much longer. The Andromeda Galaxy is approaching our own Milky Way at about 110 kilometers per second, and in roughly 4 billion years, the two galaxies will collide and merge, dramatically reshaping both. The Pleiades stars are young, perhaps only 100 million years old, and still surrounded by remnants of the dust cloud from which they formed. Looking at stars is looking backward in time, Juan says, settling into a chair someone has brought out. That light from Andromeda left its source 2.5 million years ago, when our ancestors were early hominids in Africa, using simple stone tools. The light we're seeing now shows Andromeda as it was then, not as it is now. This time delay effect becomes more dramatic with distance. The most distant objects visible to large telescopes show the universe as it was billions of years ago, not long after the Big Bang. Astronomers studying distant galaxies are quite literally observing ancient history, watching the universe when it was young, when the first stars and galaxies were forming. It's humbling, I say, to think about these scales. The crystal caves record 500,000 years of Earth history, which seems vast. But that's nothing compared to stellar and galactic timescales. Elena nods thoughtfully. Yet both are comprehensible to human minds. We can't directly experience these timescales, but we can measure them, calculate them, understand the processes operating over them. That's the power of science. It extends our senses and reasoning far beyond their natural limits. The evening has grown properly dark now, and the Milky Way is visible as a luminous band arching across the sky. Out here, with no artificial light for many kilometers, the view is stunning. The sky appears crowded with stars, far more than you can see from any city or even most rural areas. The galactic disk is clearly visible, with dark lanes of dust blocking light from stars beyond and bright patches where star formation is actively occurring. The crystals in the cave and the stars in the sky are made of the same fundamental particles, Juan muses. Protons, neutrons, electrons, all assembled in different configurations. Calcium and sulfate in the crystals, hydrogen and helium mostly in the stars, but all of it forged in stellar furnaces at some point in cosmic history. He's referring to the process of stellar nucleosynthesis, the fusion reactions in stars that create heavier elements from hydrogen. Hydrogen, helium, and traces of lithium formed in the Big Bang, but everything else, carbon, oxygen, silicon, iron, calcium, all the elements that make up Earth and our bodies, was created in stars and dispersed into space when those stars died, either gradually through stellar winds or catastrophically in supernova explosions. "We're literally made of stardust," Elena adds. It's not just poetic language, it's literal fact. Every atom in your body except hydrogen was forged in a star that lived and died before our solar system formed. The iron in your blood, the calcium in your bones, the oxygen you breathe, all stellar products. The group falls into contemplative silence, gazing upward. There's something profound about this realization, this connection between ourselves and the cosmos. We're not separate from the universe, but part of it, products of its evolution, made from materials it created and cycled through generations of stars. A satellite passes overhead, a moving point of light crossing the field of stars, a reminder of human technological achievement, of our species' tentative steps beyond our home planet. In orbit right now are thousands of satellites, a few space stations with humans aboard, and numerous pieces of debris from decades of space activity. We've barely left Earth's immediate vicinity, yet we've learned an enormous amount about the universe by doing so. The James Webb Space Telescope is revolutionizing astronomy, Elena says, tracking the satellite with her eyes. Its infrared vision allows it to see through dust clouds and observe the most distant, earliest galaxies. We're learning about the universe's first billion years, watching galaxies form and evolve, studying exoplanet atmospheres. Every week brings new discoveries. Exoplanets, planets orbiting stars other than our sun, have gone from theoretical possibility to confirmed reality with thousands of examples. We now know that planets are common, that most stars have planetary systems, and that Earth-sized planets in habitable zones where liquid water could exist are relatively abundant. This dramatically increases the potential locations where life might arise. Finding evidence of life beyond Earth would fundamentally change human perspective, I say. Even if it's just microbes on Mars or Europa, it would tell us that life is not unique to our planet, that it arises wherever conditions permit. Juan nods slowly. That's why the extremophiles in the crystal caves are so important. Every time we find life in an unexpected place on Earth, every time we discover organisms surviving in conditions we thought were too extreme, we expand our understanding of life's possibilities. We learn what to look for elsewhere. The evening air has grown cool enough that people begin to drift back inside, seeking warmth and dinner. The telescope remains set up for anyone who wants to continue observing, but the main gathering moves indoors. We follow, entering the research station's common room, where the warmth and smell of cooking food are welcoming after the desert chill. Dinner is communal and relaxed. A large pot of stew made with local ingredients, fresh bread someone baked this afternoon, a simple salad. The conversation flows easily among the researchers, mixing scientific discussion with personal stories, plans for upcoming fieldwork, friendly debates about interpretation of data. There's a camaraderie here that comes from shared purpose and the slight isolation of working in a remote location. I find myself seated next to a geochemist named Carlos, who's been studying the trace element composition of the crystal cave waters. He's passionate about his work, explaining how minute concentrations of elements like strontium, barium, and rare earth elements can reveal the history of water-rock interactions that occurred as groundwater moved through the subsurface. Water is an incredible solvent, Carlos explains between bites of stew. As it flows through rock, it dissolves tiny amounts of nearly everything it contacts. The specific cocktail of dissolved elements tells us what rocks the water passed through, how deep it circulated, how hot it got, how long the journey took. It's detective work, piecing together the water's biography from chemical clues. He shows me graphs on his tablet, plots of element concentrations that mean little to me but clearly tell him a detailed story. This signature, he points to a cluster of data points, indicates the water interacted with volcanic rocks at some point, probably deep in the system where intrusions of magma-derived rock exist. And this ratio here suggests mixing between waters from different sources, one that circulated deep and hot, another that was shallower and cooler. The complexity of subsurface hydrology is staggering. Water doesn't just sit in underground lakes, it's constantly moving, flowing through interconnected networks of pores and fractures, driven by pressure gradients and density differences. Waters of different ages and origins mix and react with rocks, creating chemical gradients and spatial variations that reflect the system's three-dimensional structure and history. One of the most interesting findings, Carlos continues, is that the water in the crystal caves is ancient, thousands to tens of thousands of years old based on radiocarbon dating. It fell as rain on these mountains long ago, percolated downward, got trapped in deep aquifers, circulated slowly while being heated and chemically altered, and finally ended up in those cavities where conditions were perfect for growing giant crystals. The idea that the crystals grew from ancient rainwater, water that fell when mammoths still walked the earth, adds another dimension to their story. Everything connects: surface climate affecting rainfall, geological structure determining flow paths, geothermal heat from cooling magma providing energy, chemical reactions with rock creating the mineral-saturated conditions, and finally, the patient accumulation of calcium sulfate molecules into crystalline lattices over hundreds of millennia. After dinner, some people settle in with books or laptops. Others gather around a chessboard. A few return outside to continue stargazing. The rhythm of life here is slower than in cities, more intentional. Without the constant connectivity and stimulation of modern urban life, people seem more present, more engaged with immediate surroundings and companions. Juan invites me to his office, a small room filled with rock samples, reference books, maps, and photographs covering the walls, images of the crystal caves from different angles and time periods, documenting both their beauty and their gradual deterioration. He pours 2 cups of tea from a thermos, and we settle into comfortable chairs. "What strikes you most about what you've seen today?" he asks. I consider the question carefully. "The time scales," I say finally. "The way processes operating over such vast periods create structures we can witness in minutes, and the connections, how everything relates to everything else. The crystals connect to groundwater, which connects to climate, which connects to mountain building, which connects to plate tectonics. Nothing exists in isolation." Juan smiles. That's exactly it. Geology teaches systems thinking. You can't understand any single feature without understanding its context, its relationships, the processes that formed it and continue to affect it. And the time scales force perspective. They remind us that our human concerns, as important as they feel, are brief moments in much larger stories. He pulls a book from his shelf, a worn copy of John McPhee's Annals of the Former World, and reads a passage about deep time, about how understanding geological timescales changes your perception of landscape. The words are beautiful and melancholic, describing mountains as ephemeral, continents as temporary configurations, Earth's surface as a constantly rewritten manuscript with each new chapter partially erasing previous ones. "When I stand in the crystal cave," Juan says quietly, "I'm standing in a library that Earth wrote over 500,000 years. Each crystal is a volume, each growth layer a chapter. We're learning to read that library, but we've only just begun. There's so much encoded there about climate, about subsurface processes, about life's adaptations, about planetary evolution. And we're racing against time to study it before it's inaccessible, I add. Yes, which is why the work feels urgent despite the geological patience we're studying. We have maybe a decade, perhaps two, before economic realities force the mind to close and the caves reflood. That's barely enough time to ask the right questions, let alone answer them all. We sit quietly for a moment, sipping tea, and I find myself reflecting on the strange privilege of being here, of having descended into those crystal depths, of being part of this brief window of human access to geological wonders that existed in darkness for 500,000 years and may return to darkness soon. Tell me about your first time in the cave, I asked Juan. What was that experience like? His eyes take on a distant look, remembering. It was 2003, just a few years after the discovery. I was a graduate student then, and my advisor had secured permission to study the cave. I'd seen photographs, read the initial scientific papers, but nothing prepared me for the reality of it. He describes suiting up in the protective gear, feeling apprehensive about the extreme heat, wondering if the photographs had been exaggerated or somehow manipulated. Then stepping through that final door and seeing the crystals for the first time. The shock of recognition that this was real, that nature had actually created structures on this scale. I stood there for probably 5 minutes just staring, Juan recalls, not even thinking about the science, just experiencing pure wonder. My advisor had to remind me we only had 20 minutes and needed to start taking measurements. But in that first moment, I wasn't a scientist. I was just a human being confronted with something that exceeded my imagination. That sense of wonder, he explains, has never entirely faded despite hundreds of visits to various crystal chambers. Each time carries some echo of that first encounter, some reminder of why he chose this work, why he's devoted his career to understanding these formations and fighting for their preservation. The crystals taught me patience, Juan continues. In graduate school, I wanted quick results, publishable findings, career advancement. But studying something that grew over 500,000 years forces you to slow down, to think in longer time frames. A research project might take 5 years. That's nothing compared to the timescales we're investigating. He tells me about the community of researchers who study the Naica caves. Geologists, microbiologists, crystallographers, geochemists, climate scientists, all bringing different perspectives and techniques to understanding these formations. They meet annually at conferences, share data, collaborate on papers, and collectively build knowledge that no individual could achieve alone. Science is ultimately a collective endeavor, Juan reflects. We build on work done by previous generations, contribute our own pieces to the puzzle, and leave a foundation for future researchers. The crystals have been here for 500,000 years. Humans have known about them for only 25. Imagine what we might understand about them in another century if we can maintain access and continue studying them. The conversation drifts to broader questions about geological preservation, about which features deserve protection and how to balance scientific access with conservation. There are no easy answers. Every situation involves trade-offs between competing values and practical constraints. Sometimes I wonder if we're too focused on preservation, Juan muses. Everything in geology is temporary on long enough timescales. These crystals will eventually dissolve back into water, the rock will erode, new formations will appear elsewhere. Maybe our role isn't to preserve everything but to understand it, document it, learn from it, and accept that change is fundamental to Earth's nature. Yet, even as he says this, I can hear the conflict in his voice. Understanding the inevitability of geological change doesn't eliminate the desire to protect remarkable features, especially when human activities accelerate their destruction or alteration. The crystal caves would naturally exist for many more millennia if left undisturbed, but mining operations shortened their accessible lifetime to mere decades. What would you want people to understand about the caves? I ask. If you could communicate one thing to the wider world, what would it be? Juan thinks carefully before responding. That patience and time can create beauty beyond human imagining. We live in an era of instant gratification, of rapid change, of constant stimulation. The crystals remind us that some processes can't be rushed, that slow accumulation over vast time produces results that quick actions never could. That lesson applies to more than just geology. It applies to relationships, to learning, to social change, to ecosystem restoration. He pauses, then continues, and also that we're part of Earth's story, not separate from it. The same physical laws that governed crystal formation govern our bodies. The same atoms that make up those crystals make up us. We're not observers of nature from outside. We're participants in it, products of it, subject to its constraints and opportunities. The evening has grown late, and I can feel the day's experiences settling into memory, the physical sensations of heat and exertion fading, while the visual impressions and insights remain vivid. Juan walks me to the guest quarters where I'll spend the night, a simple but comfortable room with a window overlooking the desert. Thank you for sharing this place with me, I say sincerely, for your knowledge, your passion, your time. Juan smiles warmly. Thank you for your interest, for asking good questions, for understanding why this matters. Every person who visits and truly sees what's here becomes an advocate for preservation, for science, for the value of understanding Earth's wonders. That advocacy is crucial. After Juan leaves, I stand at the window for a long time, looking out at the desert under starlight. The landscape is serene, painted in shades of silver and shadow, the distant mountains dark silhouettes against a sky crowded with stars. Somewhere below this surface, deep in the earth, those magnificent crystals rest in their chamber, slowly changing, slowly losing their pristine clarity, waiting for the day when water will reclaim them. I think about the journey those crystals represent, not just their own formation over 500,000 years, but the larger journey of matter and energy that brought their constituent atoms to this place. The calcium and sulfur that make up selenite were once part of ancient marine organisms, creatures that lived and died in seas that covered this region hundreds of millions of years ago. Their shells and bodies settled to the seafloor, were buried, compressed into rock, then partially dissolved and transported by groundwater to the crystal cave where they crystallized into new forms. Those same atoms will continue their journey. When the crystals eventually dissolve, whether in decades or millennia, the calcium and sulfate will return to groundwater, flow through rock, perhaps precipitate again in different forms, or reach the ocean where they might be incorporated into new organisms. Nothing is permanent except change itself. The endless cycling of matter through different states and structures. I prepare for sleep, the day's experiences replaying in my mind, the descent into heat, the first sight of those massive translucent beams, the smaller crystalline rosettes of the ice palace, the fluid inclusions containing ancient microbes, the surface outcrop with its tiny calcite crystals, the evening astronomy session connecting Earth to cosmos. Each moment felt significant, part of a larger pattern of discovery and understanding. As I lie in bed, I become aware of the profound quiet. Unlike the crystal cave with its oppressive heat and humidity, this room is comfortable, temperate, but both share a quality of stillness, of separation from the ordinary flow of daily life. In this isolated research station, surrounded by desert, far from cities and their constant activity, there's space for thought to expand, for perspective to shift. Sleep comes gradually, gently, and my dreams are filled with crystals, not the giant selenite beams, but smaller formations, growing and dissolving in time-lapse, showing the patient accumulation of matter into structure. I dream of water flowing through darkness, carrying dissolved minerals, seeking spaces where chemistry and physics align to create solid beauty from liquid solution. I dream of time itself made visible, each crystal layer a frozen moment, the whole formation a record of duration beyond human comprehension. In the dream, I understand something I hadn't quite grasped while awake, that crystals are time made tangible, that their growth is the physical manifestation of patience, that their geometry is mathematics expressed in matter. They bridge the abstract and concrete, showing how universal laws manifest in specific forms, how the invisible realm of atoms and forces becomes visible structure. The dream shifts, and I'm floating in space, looking down at Earth from orbit. The planet is beautiful, swirled with clouds, spotted with the brown and green of continents, mostly covered by the deep blue of oceans. From this distance, there's no sign of the crystal caves, no indication of the geological complexity beneath the surface. Earth appears simple, serene, a single unified system. But I know the complexity is there, hidden from this perspective, but real. The layers of rock recording billions of years of history, the flowing mantle carrying continents on its slow currents, the inner core of solid iron surrounded by liquid metal, generating the magnetic field that protects life from solar radiation. Complexity within complexity, systems nested within systems, all of it interconnected and interdependent. The dream fades, and I drift into deeper, dreamless sleep, my breathing slowing, my body relaxing completely into rest. The desert night is perfectly still outside, the stars wheeling slowly overhead in their ancient patterns, the earth rotating on its axis at 1,000 miles per hour, though nothing seems to move. Everything is in motion, yet appears still, changing, yet seemingly changeless. The paradox of geological time, where transformation happens too slowly for human senses to detect directly, but accumulates into dramatic changes over sufficient duration. Hours pass. The stars shift position. The temperature drops further as the desert radiates heat to space. Small nocturnal creatures go about their business, hunting, foraging, mating, living out their brief lives under the vast, indifferent sky. In the crystal cave deep below the surface, water vapor continues to slowly strip molecules from crystal surfaces, the deterioration progressing grain by grain, molecule by molecule, imperceptibly but inexorably. I wake gradually to soft light filtering through the window, dawn arriving over the desert, painting the eastern sky in shades of rose and gold. For a moment, I'm disoriented. Then memory returns. The research station, the crystal caves, yesterday's journey into Earth's hidden depths. I lie still, savoring the peaceful transition from sleep to waking, feeling rested in a way that goes beyond physical renewal. Rising, I dress and step outside into the cool morning air. The desert is transformed by the soft light of sunrise, every rock and plant casting long shadows, the mountains glowing warm in the distance. A few early birds are active, A roadrunner crosses the open ground with its characteristic stride. A raven calls from somewhere unseen. The day is beginning, and with it, the station is stirring to life. In the common room, I find Juan already awake, making coffee and preparing for the day's work. He smiles when he sees me, gesturing to the pot. "Sleep well?" "Remarkably well," I tell him honestly. "I dreamed about crystals, about time made visible." He nods as if this is a common occurrence. "The caves have that effect. They get into your mind, change how you think about time and formation, about patience and beauty. Many visitors tell me similar things, that they dream about crystals afterward, that the experience stays with them." We drink coffee together in comfortable silence, watching through the window as light spreads across the landscape. Other researchers begin to appear, the station coming fully awake, the rhythm of another working day beginning. There's field work to do, samples to analyze, data to process, papers to write, the ongoing work of science, incremental and patient, building knowledge piece by piece. "Will you visit the cave again before you leave?" Juan asked. I consider this. Part of me wants one more encounter with those magnificent formations, one more opportunity to stand in that space and feel the weight of geological time. But another part feels that yesterday's visit was complete, that returning would somehow diminish rather than enhance the experience. "I think once was enough," I say finally. "I'll carry the memory with me, and maybe that's better than trying to recapture the initial impact." Juan seems to understand. The first time is always the most powerful. Subsequent visits bring different rewards. You notice details you missed, you understand connections you didn't see initially. But that first encounter, that sense of wonder and discovery, is unique. After breakfast, I prepare to depart, packing my few belongings, saying farewell to the researchers I've met. Each one offers a different perspective on the caves and their work. Carlos, with his geochemical detective stories, Elena, with her meteorite connections to cosmic history, others with their own specializations and insights. Together, they form a community dedicated to understanding this remarkable place before it becomes inaccessible. Juan drives me back toward civilization, the research station receding behind us, the desert landscape rolling past. We talk less now, both of us absorbed in our own thoughts. I find myself already nostalgic for the experience, even as it's still happening, aware that this brief window into a hidden world is closing, that I'm returning to ordinary life, that the crystal caves will continue their slow transformation whether I think about them or not. "What will you do next?" I ask Juan as we approach the point where I'll catch transport onward. "What questions remain to be answered?" "So many," he says with a slight laugh. "We're still working on dating the crystals more precisely, understanding exactly when they began forming and whether growth was continuous or episodic. We're studying the microbes in more detail, trying to understand their metabolic capabilities and how long they can remain viable. We're monitoring the deterioration rate to determine if any intervention is worthwhile. And we're trying to document everything as thoroughly as possible, knowing access won't last forever." The vehicle slows, reaching the junction where our paths diverge. Juan pulls over, and we step out for final farewells. The desert stretches away in all directions, vast and ancient, holding its secrets beneath an innocent surface. "Thank you," I say again, inadequately, "for everything you've shown me, taught me, shared with me." Juan clasps my hand warmly. "Thank you for caring enough to visit, to ask questions, to try to understand. The crystals will endure for a while longer, whether humans witness them or not. But witnesses matter, They carry the story forward, help others understand why these places are precious, why the work of understanding Earth's wonders is worth doing. We part ways, and I watch him drive back toward the research station and the caves beneath. I turn toward my own journey, carrying with me memories of translucent giants in hidden chambers, of time made visible in crystalline form, of patient accumulation creating impossible beauty, of Earth's capacity to surprise and inspire even after billions of years of existence. The caves taught me what I suspected, but needed to experience directly. That wonder is always available if we look deeply enough, that beauty operates on all scales from atomic to cosmic, that understanding enriches rather than diminishes appreciation, and that patience, given enough time, can create miracles. As I settle into my journey home, I feel grateful for this brief intersection with something ancient and extraordinary, for the privilege of having stood in that crystal cathedral, for the reminder that Earth still holds secrets, that discovery is ongoing, and that the universe, including our own small planet, is far more remarkable than we typically imagine in our daily lives. The memory of those crystals will stay with me, I know, surfacing in quiet moments, reminding me to slow down, to appreciate patient processes, to see the extraordinary in what might seem ordinary. And perhaps that's the greatest gift the caves offer, not just their beauty, but the shift in perspective they create, the invitation to see time differently, to recognize our brief human span as part of much longer stories. Thank you for joining this journey into Earth's hidden crystal palace, into the depths where time becomes visible and patience creates beauty beyond imagining. If these stories of science and wonder help you find peace and rest, please consider subscribing to our channel. Each tale we create is an invitation to slow down, to marvel at our remarkable universe, and to drift gently into sleep with a sense of connection to something larger than ourselves. Rest well, dream deeply, and know that Earth continues its ancient work of transformation, creating new wonders even as we sleep.